Welcome. This lecture is called Nonsingular Matrices. The definition of nonsingular matrix is plays a substantial role in linear algebra. And before we visit this definition, we're going to refresh our mind with what is considered to be a square matrix. In general, the arrays of numbers that we're calling matrices are rectangular. That is when either the number of rows exceeds the number of columns, or when the number of columns is larger than the number of rows, then the matrix is considered rectangular. However, when the number of rows matches the number of columns, when there are as many rows as columns, then we will consider this scenario, we'll consider that type of matrix as a square matrix. So with this in mind, we consider this definition. So suppose the matrix A is such that the number of rows and columns match. It is a square matrix. And also suppose that that matrix is the matrix of coefficients of a homogeneous linear system of equations, as we have here. Furthermore, assume that the solution set for the homogeneous system of equations with that matrix A as the matrix of coefficients is the trivial solution. The trivial solution and the trivial solution only is the only member of this solution set. So in such case, we would classify the matrix, this square matrix, as a non-singular matrix. For all other cases, we would say that A is singular. In other words, when the solution set of this homogeneous system of equations contains other solutions besides the trivial solution, then we would classify A as a singular matrix. So to determine or classify the singularity, the so-called singularity of a matrix, we will have to deal with the calculation of a solution set of a linear system of equations. In other words, we always have to construct a very specific system of equations, and we have to review the solution set of such homogeneous system. So 2 points to be underscored here. We can decide non-singularity of any square matrix, and the determination of non-singularity requires calculation of the solution set of a certain homogeneous system of equations. And here we have an example. Suppose this is a 3 by 3 square matrix, 3 rows, 3 columns, and suppose we consider this as the coefficient matrix of a homogeneous system. In other words, we would augment this matrix with a column of zeros, and therefore we proceed to row reduce the augmented matrix, and so we would obtain the following. Okay, we would obtain this being the RREF of the augmented matrix, with a last column being the column of zeros. And because of this shape, right away, we can draw a conclusion. That conclusion being that in this case, little r is equal to 2, the number of non-zero rows, while the number of columns of the original matrix of coefficients is 3. And because n minus r is not 0, then what we expect here is precisely a scenario in which the solution set of that homogeneous system contains infinitely many solutions. Okay, infinitely many solutions. So we could do what we always do. We decide, we could write down the set D, and then write down the set F. Okay, and so D is going to contain indices 1 and 2, and F will contain indices 3 and 4. In this case, we would consider the variables x1 and x2 as the so-called dependent variables. And in fact, by looking at each of these rows, we would say, okay, 1x1 plus 0x2 plus 1x3 equals 0, which means that x1, being the dependent variable, is written as minus x3. And also from the second row, we would write 1x2 minus 1x3 equals to 0, from where we write x2 equals to x3. So we have an expression for x1, one of the dependent variables, in terms of the free variable x3, and another expression for x2, the other dependent variable, in terms of the free variable x3. So this leads to writing a solution set that looks like this, where x3 would be the free solution, but very importantly, because this, well, here, this would be the null space of the matrix A, and now you can see that precisely the null space of this matrix is directly related with the definition of singularity. The fact that this null space contains non-trivial solutions there, non-trivial vectors, that is directly related with the fact that this matrix is singular. If the null space of the matrix, or the solution set of the homogeneous system, this homogeneous system, if that set contains only the vector of zeros, then we would say the matrix is non-singular. So here we have another example. This is a 3 by 3 matrix. We augment this matrix with a column of zeros. We're considering here the linear system that has this as the matrix, this matrix as the matrix of coefficients, and the zero vector. We're also considering the calculation of the null space of this matrix. Okay. And based on what we obtain here, this is an area in which little r, number of non-zero rows in RREF, is 3. Number of columns is also 3. They match. Okay, and what we can read here from each of these rows in the RREF is that the solution set of this homogeneous system is exactly x1 equals 0, x2 equals 0. That's exactly the information you read from each row here. This would imply that you have 1x1 plus 0x2 plus 0x3 equals 0, and then the second row would imply that x2 equals 0. The last row would imply that x3 equals 0, and that leads to having this set as a solution set of the homogeneous system, and also leads precisely the definition of the null space of the matrix. In this case, the null space of the matrix contains only the zero vector, the trivial solution, and therefore we would classify this matrix as non-singular. So non-singularity is something directly related with the null space of the matrix. A new a definition that we introduce at this time is the definition of the identity matrix. Okay, in the calculations of reduced row echelon form, we had seen part of the structure that is very peculiar, very characteristic of this matrix. This is a matrix that contains only ones and zeros, and the ones appear on entries of the matrix such that the row number and the column number are the same. Those entries are called the diagonal entries. Okay, those entries are precisely the entries on this illustration for a 4 by 4 identity matrix, are precisely the entries that appear on the so-called diagonal of the matrix. You may want to think of this as being a square, right, equal number of rows and columns, and then the entries that appear on this region of the square are the so-called diagonal entries. Okay, and for those entries, here you have, say, row I, and here you have column J, but it happens that the diagonal is such that J equals I. Okay, or you can say that I equals J. So the row number and the column number are the same. These entries are going to be on, row 1, column 1, row 2, column 2, row 3, column 3, all the way through, I don't know, row 100, column 100. So row number and column number, they are always matching. And so those are the entries that appear on this part of the matrix. And so when we were computing reduced row echelon form, this was the aim. The aim was to make the matrix look as similar as possible to an identity matrix, which has the property of having ones along the diagonal and zeros everywhere else. So if you look at the structure of this matrix, there are zeros above 1, below 1 on every entry on the diagonal, and then there are zeros to the left on one given row. There are zeros to the left of that one. There are, in this case, happens that there are zeros also to the right.